All right, let's read the problem. Let S be the boundary of the region enclosed by the positive cone. This is a cone, remember that. Z equals the square root of x squared plus y squared, because z squared equals x squared plus y squared consists of two cones, right? So this is a half cone. And the second bittersweet curve, bittersweet surface is a sphere, right? So here's the graph. This is the graph of this question of the surface. So as you can see, this is a half cone, and this is the top part of the sphere. That's it. You have questions? So the top spherical shell is x squared plus y squared plus z squared equals 2 squared. 4 is 2 squared. So what is the radius of this sphere? It's 2, right? And this is the conic surface. So can you tell me what this angle is? So with this here, what this angle is that 90 degrees? 45. Very good. This is 45 degrees. Maybe it'll be useful for the quiz. So this is 45 degrees. In other words, pi over 4, right? Because the entire angle is pi over 2, so half of that is pi over 4. All right, that'll help us determine the bound for phi later on. Okay. How do we set up this integral? Well, our goal is to compute this given surface integral, right? This is also called the flux of the vector field. They mean the same. The flux just means the surface integral over this vector field. All right, how do we compute that? So when we see a surface integral over some surface of a vector field, our first intuition should be to apply which theorem? Yeah, should apply a theorem, right? This theorem is the divergence theorem. We have 3 big theorems: Green's theorem, Stokes' theorem, and the divergence theorem. And the only tailored theorem for surface integrals is the divergence theorem. All right. So let's apply the divergence theorem. That is circle 1 in your last formula sheet. Yeah. So the circle 1 corresponds to the divergence theorem, which says this surface integral actually equals this triple integral over B, where B is this entire solid. In other words, the boundary of B is this surface S, and the entire solid is this, B, which is a 3-dimensional solid. So the divergence of the same vector field, dot ds. I'm sorry, not dot ds. dv, right? This is a triple integral. This is what divergence theorem tells us. We know divergence. We know triple integrals, right? We're very familiar with them because triple integrals are much easier to compute than surface integrals. So we can just by this theorem, we can directly compute this triple integral instead of computing this more laborious surface integral. That's cool. All right. So to compute this triple integral, we have to compute this divergence, right? This div f. How do we compute that? We can directly use the definition, nothing fancy here. So by the definition, circle 2, the divergence of f, this is circle 1, the divergence theorem, and this is circle 2, the definition. The definition says the divergence of f actually equals the partial derivative of the first component of f plus partial y times the second component of f plus partial z, the third component of f, right? Let's write that down. So it equals del over del x. So del over del x times the first component, that is this alpha component of f. Let's go. Plus del y, the second component, this bittersweet component, yx squared. Finally, del z, the third component, zy squared. That's it. That's the divergence of f. Of course, we should compute this sum of the 3 partial derivatives. Very easy to compute, right? That is just z squared plus x squared plus y squared, right? That's it. All right, so the entire surface integral is equal to this triple integral, which further equals this guy. So the triple integral over the same v of this guy, of this divergence. So let's copy this purple. This is called purple mountain majesty. I hope you'll miss these colors. Of that dv. And let me show you another funny picture. This, this shape is just like this ice cream. It says you can't buy happiness, but you can buy ice cream, and that is pretty much the same thing. I guess it's written by P. Very similar to each other. Right? All right, so let's continue to compute this triple integral. How to compute that? We could definitely use rectangular coordinates or cylindrical coordinates, right? But that's too much work. Who likes to use them? I don't like to use that. We have a better way. What is that? Yeah, if you take a look at this graph, it includes this top part of a sphere, right? So we have another coordinate system tailored to spheres called spherical coordinates. That's what we're going to use. So let's use circle 3, part S, which is the cylindrical, the spherical coordinates part. So that's it. We have this formula. You can find that formula in your formula sheet. So let's compute this triple integral using spherical coordinates. So what is that? Well, I have included a very good way, actually the best way I know, to determine the limits of this integration of the integration in this spherical coordinate system. So it consists of 3 parts. First of all, we determine this theta. Of course, you could determine the second polar angle phi first, but the order of the first two actually doesn't matter. So, but I like to first determine the angle theta. So how do we determine that? We set theta by rotating a half plane. So we can imagine there's a half plane around the z-axis from 0 to 2 pi, noting the first and last points of intersection within the region. So usually when there's an entire circle or disk, theta usually always ranges from 0 to 2 pi. Question? Okay. So first, theta ranges from 0 to 2 pi. Please know how to do that. That'll be related to your quiz. So 0 to 2 pi d theta, that's the first one. Let's use another color. Of course, make the color match to your formula sheet. So this is d theta. All right. So second, let's determine the second variable phi in the spherical coordinate system. So let's use this bittersweet color for phi, d phi. What's the range of phi? Well, let's follow the second bullet point. We determine phi by envisioning the unfolding of a morning glory flower like that. There's a flower, which lower vertex is at the origin, so it's placed this way. And you can imagine the unfolding of this flower. In other words, the angle moves from the z-axis down to the xy plane, like this dynamic process, right? So it'll first touch this polar cone. That is, it'll first touch phi equals 0, because in the spherical coordinates, this half cone represents phi equals 0, and this half cone represents phi equals which angle? It's computed together, pi over 4, right? So phi ranges from 0 to pi over 4 d phi. That's perhaps the most important part, the most difficult part in this problem. And also it'll be the most difficult part in your quiz. So make sure you know how to do that. Make sure you understand this. Again, because this z-axis in the spherical coordinate system corresponds to phi equals 0. That's why the lower bound for phi is 0. And this line, this half cone with this angle pi over 4, that is the cone in the problem, in the graph. The graph corresponds to phi equals pi over 4, because this is pi over 4. That's why the upper bound is pi over 4. Is that clear? Yeah, that's good. So d phi. All right, last, we determine the bounds for rho. This is actually the easiest one. d rho. So because the radius of this sphere is 2, rho ranges from 0 to 2. That's it. Of course, you can also follow the last step. Determining rho, you can identify. You can imagine there's a ray from 0 that intersects the region E. In this case, this is the entire solid is the region E, and we can note this A for the initial contact and B for the final contact within the volume. In other words, if you draw a ray within the solid E, then this ray will first touch this rho equals 0. That is the origin, right? Because the solid starts from the origin. And then this ray will touch this upper surface spherical shell. That corresponds to rho equals 2, because again, the radius of the sphere is 2. That's why rho varies from 0 to 2. That's it. Any questions? Yeah.
I think I understand that from like the center to the edge of the cone, like that angle is pi/4, but like algebraically, how do we find that?
Yeah, that's a very good point. You can find it this way actually. If you, very good point. If you draw this, extract this XZ plane from this 3D space, so you can draw a graph like that. You can consider this surface level at this point y equals 0. That is, we have this following XZ plane. So what is the graph? The level surface on this XZ plane, well, it just looks like that, right? Because in this plane, y equals 0. Great, because we just take y to be 0, and then we get this plane. All right, so if you set the value of y to be 0 in this equation, we're going to get z equals the square root of x squared plus 0. What is that? Z equals x, right? So if you set y to be 0, we're going to get z equals the square root of x squared plus 0. That is just x, because we're considering the other column. All right, z equals x in the xz coordinate system. You know what this angle is, right? It's pi/4. Because the slope of z equals x is 1. In other words, the slope here is 1. The slope is defined as the tangent of this angle of inclination. That is tangent of pi/4 equals 1. That's why this is pi/4 algebraic. Is that?
Yeah.
All right. So we're almost done. But have I finished yet? Is that the final answer? Yeah, this is a very good. This is a very minor yet important point. We have to add the Jacobian here. That is rho. That is rho squared sine phi. And then we copy this previous integrand, which is this guy. And what is this guy? It's a spherical coordinate system. Yeah, very good. By the node below this circle 3s, z squared plus x squared plus y squared is nothing but rho squared, right? Very easy in the spherical coordinate system. So we write rho squared here. That's it. So by this is by circle 5 node. Circle 3s node. Yeah, so that's the final answer. Again, please don't forget to add this rho squared sine phi. Very important point. Yes?
On your quiz, do we solve it out, or can we just write that?
Yeah, on your quiz for the first problem, you have 2 quiz problems. For one of them, you don't have to solve. You don't have to evaluate that. You only have to write it as an iterative interval. But for the other, you have to evaluate. That is for question 1. You'll have to, for question 1, you don't have to evaluate anything. For question 2, you'll have to compute this answer until the final step. All right, so let me say one more. Let me say one more thing about that. So the bottom part. Let's see. The bottom part. This last line is similar to quiz problem 1, and the first line is similar to quiz problem 2. And this graph is similar to quiz problem 1. That's it.
Wait, can you repeat that?
Yeah, I'm reading them down. The bottom line will be similar. How similar? I will tell you. similar to quiz problem 1. And this line is similar to quiz problem 2. This entire graph is similar to quiz problem. All right, I'll give you about 5 or 6 minutes to do that, and then I'll show you the answer and the solution, the entire solution. All right, let me know if you have questions. All right, let me show you the solution to this question, the final solution. Before that, let me show you some funny pictures. Polar coordinate system, rectangular coordinate system, cylindrical polar bear, and spherical polar bear. Right? So calculus can be very fun, right? Life can be very easy. And learning can be very easy and fun. All right, let me show you the entire solution. That's it. So that's the final answer. As long as you know how to do that, I'm sure you'll nail the quiz. The quiz is actually even easier than this question. And yeah, the graph is almost the same as the quiz graph.